In this lecture, we are going to look at chemical mechanical polishing. So chemical mechanical polishing is a process that we use to make wafers flat. So let's look at why we want to make it flat and why the wafers are not flat to start with. So here we see two scenarios. There is scenario A and scenario B. So in scenario A, we have a trench, and we are trying to fill up the trench using conformal deposition. So this is the starting cross section. So what we are looking at is the cross section on the wafer. So we have a trench, and then we start filling the trench with a material which is conformally filled. So what is the meaning of conformal? So the thickness, the vertical and horizontal thickness, let's say this is h and h dash, so this should normally be equal. Okay. So if we have a uniform thickness coating both at the top and the side wall and the bottom, we call this as a conformal deposition. So this is good for many applications, but then if you want to fill this trench, you normally end up with a topography like this, right? You won't get a flat surface here. And if you want to put circuits on top of this layer, you will transfer whatever topography that we have here. So this is the case of a trench. But now let us look at an isolated line here, and we have space at the sides, right? And here again we start with a conformal deposition process where we deposit the material around, and then we increase the thickness. But then if we increase the thickness, we end up with this sloped sidewall, and it's not going to be flat. So this is going to be a problem if we want to build circuits on top of this. Not necessarily a large number of layers. Even if you want to do one additional layer, the topography here could cause serious issues. And let's look at some general expectation from the wafer fabrication process. So what are all the issues that we face when we build multi-layer stack, right? So we tend to use conformal deposition, which gives you very good fill, right? But this normally results in a topography. That means it's not going to be flat anymore. So that's what we call non-planar surface. And this is the result of such a conformal deposition, right? So you always have this sort of neck that is formed, and then the subsequent layers are going to also follow the same topography, right? And if that is the case, your layers are not going to be of equal thickness. For instance, this black region is a metal region, but if you look at the metal thickness here and the metal thickness here, this is going to be different, right? And then you see a section here that could result in failure because the resistance in this particular contact is going to be very high, right? And you could have serious failures here. But ideally what we want is this sort of flat geometries, right? So you want everything to be flat to start with. So you complete, let's say this is the front end, and this is your contacts, and after doing the contact you want to make the surface flat, and then you go for metal 1, and then this is via 1, and then you also make it flat, and then you go for metal 2 and via 2 and so on, right? And in order to achieve this, you are using two type of material. One is a metal and the other one is dielectric. So you want to make sure that you will be able to create this flat surface while having metal and dielectric in place, right? So there are some alternate methods to address this topography issue. There is something called spin-on deposition, and there is something called etch-back and reflow. But there are disclaimers once we start using this. For instance, you cannot use all the material that you require as spin-on deposition. For instance, you can deposit dielectrics using spin-on, but you won't be able to do metal deposition using spin-on. Similarly, reflow. So reflow meaning you nearly melt the material. Right? Once you melt the material, a solid material, it tries to reflow and then becomes flat, right? So Metal and dielectrics, they require very high temperature. The thermal budget of your process won't allow you to heat up this material. So you won't be able to do this reflow also. So we need to look for better ways to make this surface flat. So why do we need this planarization? So there are functional and parametric yield issues related to this flatness. The one important thing is depth of focus. This is something we saw in optical lithography, where your focus onto the surface is very important, because this is where the image is going to be very sharp. But if you have a surface that is non-planar, then your focal point is going to be very different. For instance, if you are going to align it to the surface here, but then in this case it will be out of focus. So this is out of focus and this is in focus, right. So you want a surface to be flat, and this could result in lithography challenges. And the next thing is parametric yield, right. So we saw in the earlier slide the metal line thickness is varying, right, and in some cases the whole cross section can be very different, and this would result in resistance change, and this resistance change would also bring in delays, right. So if you have multiple metal lines connecting different transistor blocks or different functional blocks, if you want to transmit and receive data that is synchronized, if you don't have the uniformity, you are going to have timing errors, right. It will be very difficult to adjust. So we want the metals to be uniform in cross section. So for that you need a flat surface. And the next thing is the failure of contacts also, right. So we saw a case where if you have a topography and if your metal is very thin, where you are making contacts, and this is a failure point, right. So you want to make sure that you don't have these kind of failure points while you are connecting two metal layers. So this could result in open circuit at some point, or it could result in reliability issues, right, where you could have very high current crowding there, and then you will start seeing electron migration and other effects, right. So you want to make sure that you avoid these scenarios that could result in failure or suboptimal operation of your chip, but at the same time your subsequent processes should not be affected. In this case, you don't want lithography to be suboptimal because you don't have a flat surface. And for that we use chemical mechanical polishing. As the name suggests, we use chemicals and then we use mechanical force to do polishing. Okay? And the setup has these four critical elements. One is a polishing head, right. So you want a polishing head where the wafer is loaded, and then you have a polishing pad, right, and then you have a conditioner, and then you have a slurry. So these are all the four elements that is required to do chemical mechanical polishing, or in short form we call it CMP. Okay. So what we see at the bottom image is a cross section of how we do chemical mechanical polishing. So this is the polishing head, right. So this is the polishing head, and the wafer is put upside down, right. You can see the topography here, right. So you have the topography here. It's a non-uniform coating of silicon dioxide on, let's say, silicon, and it is held by this head, right. So you have the carrier that is holding the wafer, and then it is pressed, right. There is a force applied, and then it is pressed to a pad. This is a soft pad that is put on a very hard plate, and this plate is can be rotating, right, and your head can also be rotating, and the soft pad is the one that is going to flatten or polish this topography. Okay. And then what we have is a conditioner, right. So the pad can become smoothened over time. Okay. This is similar to sandpaper, right? If I give you a piece of metal with rust, right, and if we want to remove the rust and make it smooth, we rub it against a sandpaper, right? And after a while the sandpaper will become smooth because it is going to collect all the material from the rusty pipe and it will become smooth, right? And then you want to remove all these deposits on the pad, right? And that's what this conditioner is doing. So the conditioner will have this diamond tip that is going to make the pad rough so that it can remove the material from this wafer, right? And in addition we need a slurry, right, similar to sandpaper that has this particles, right, abrasive particle. You also need a abrasive here, and that abrasive is supplied by this slurry in a liquid form. So these are all the 4 elements that is required in order to do your polishing. And the picture on the top shows you the configuration, right, a perspective of how the polishing is done. So you have a very large plate that has the wafer head, and then it has a pad at the bottom, right? And this pad is the one that is going to remove the material in the presence of slurry. So slurry is dispensed onto the pad, and then the polishing head with the wafer is pressed against the pad, and then you can rotate it, right? So there are different motions. We will see that in few slides from now. So where you have the head which is rotating in one direction, and your pad is rotating in one direction, and then you also have the spindle or the head rotating in another direction. So the rotation direction and also the configurations vary from method to method, but in principle you want at least one of these elements moving so that you have friction between the wafer surface and your pad to create material removal. So let us look at CMP process, how the CMP process works, right. So let us start with a very simple structure. So let us take a very simple configuration. So I take a silicon substrate that has with a certain topography, right, and now I am going to deposit material on top of it, right. So when I deposit let us say silicon dioxide, and that silicon dioxide is going to create a topography like this, right. So in this case it becomes reasonably flat, but here you see this topography, all right. And now but the goal is to flatten this, right. So how do we flatten this? The first thing that we do is what we call the smoothing process, right. So we are going to put this through CMP process. So that means you are putting this wafer against a pad and then start rubbing, okay, in the presence of slurry, of course. The first process that happens is called smoothing, right. So you take this layer, and then what we do is as a smoothing step that will smoothen the topography, and then it should give you a layer like this, right, and this is called smoothing. So in the smoothing step you still have topography, right, you are not flat yet. But what you have done is you have converted this large topography to a very small topography, right. You are just reducing the topography, all right. And the next step is local planarization, right. So first step is smoothing, and the next step is local planarization. So this is the next process that happens while you are doing CMP, and this local planarization would do something like this. So now you have flat surface, but this flat surface in the local region it is flat, but globally it is not. So it says So, it is locally flat here and it is also locally flat here, but then you still have this topography in a global sense. So, what you have done now is, after smoothing, is a local flattening. So, if we have done local flattening now. So, the next step is to do global flattening, right. So, or global polishing. So, in the global flattening process, you will get a layer something like this, right. So, in this case you have a global flatness, right. So, after this you have global flatness now. So, this is how we do chemical mechanical polishing process scheme, right. So, when you first put the wafer into the pads and then you start polishing, the first thing that would happen is the smoothing process, right. And then once you get reasonable smoothness or reduction in the topography, in the next step you get local flatness, right. So, you do not get global flatness, you get local flatness, and then once you keep on polishing you get global flatness. So, once you achieve global flatness, the whole wafer is now flat, right. The uniformity or the flatness is what you expected. But then if you do not do global flattening, you get local flattening alone, right. But still you do get some planarization range, right, that is undesirable in many of the applications. Okay. So, this is how the CMP process progresses. Okay. So, let us look at what is the actual removal process looks like. So, what is the mechanism we use in order to do material removal. So, the material removal is the primary process, right, is the primary function in CMP, right. So, all you want to do is remove material. But then for that we use all these pads and slurries and so on, right. So, how the pad and the slurry and the pressure between the wafer and the pad affects is what we are trying to understand in this slide, right. So, the material removal rate, right. So, how much material we remove depends on the height, right. So, the height difference that we have, right, between the flat layer here and the topography here. So, the height difference and also how much time we spend in this polishing. Okay. So, that is something which is straightforward. Okay. You can also take that as a ratio and then that could give you your material removal rate, right. But it also depends on, if you look at it more carefully, right, it depends on the pressure you apply, right, which depends on the height difference. Okay. So, the pressure, there are two pressures that is depicted here, P1 and P2, right. The pressure P1 is less than P2 because of the topography, right, and that is the reason in the earlier statement we said it is the height difference that matters, or in other words it is the pressure difference that we have between the flat layer and the topography, and also relative velocity, the relative velocity between the wafer and the pad. So, this is something that you need to understand. Just by applying a pressure, right, putting them under a certain pressure is not going to help you in stationary function, right. Either wafer or pad should move, right, or both of them could move. So, you want them to move at a certain velocity. The faster they move, the removal rate is higher, right. So, the pressure and the velocity also plays a huge role in dictating the material removal rate. So, the material removal rate depends on the velocity gradient that we have, pressure we apply, and then there is a Preston coefficient or constant, right. So this constant comes from the particle that we use, the type of pad we use, and other configurations, right. So for all practical purpose, you can say that the removal rate depends on the pressure that we apply and also the velocity at which we move. And this is how the pressure distribution is going to look like, right. On the top is the wafer and the bottom is the polishing pad. This red dot is showing the pressure distribution, right. When the wafer is flat, you don't have a lot of pressure that is being applied, so there is no removal at all, right. So it is a physical process, so you are pressing against the surface, right, and then rubbing it. If the pressure is low, then your removal rate is very low. But then if the pressure is very high, because you have this topography, then you will have faster removal, or the material removal is high here, right. So as we slowly progress, your pressure is going to reduce, right. So let me draw this and tell you how this happens, right. So now I'm going to apply plate pressure here, right. This is inverted, let's say, right. And then because of the topography, I will have a large pressure here, right. Let's say this is P2, and then a smaller force here, right. And then this would result in higher removal rate at the center and lower removal rate at the outside, right. So now the first process, as we discussed, this is the smoothing process, right. So because of this large pressure in this topography, you are going to remove more material here and then almost no material in the outer section. But now if we keep on progressing, let's say this is T0 and this is T0 plus T1, let's say, and then now I keep on doing it, so I still have more pressure here because of still the topography. This is T1 plus T2, and now because the topography is reducing here, you see the topography is reducing and your pressure that you apply is also reducing now. So now after a while this will become something like this, and then this is T0 plus T3, and this is where you achieve flatness, right. Beyond this point, what you do is you keep this profile uniform, right. And then if you keep on doing it, right, so let's say I want to even do longer duration polishing, then you are actually slowly removing this whole profile. So this whole profile is going to move down, but the flatness will remain. So you will lose material, okay. So if you can stop at this time, then you will get reasonably flat without loss of material, right. So when the topography is reduced, you have a reduced force and reduced removal. So that is what this contact area is all about. If you increase the contact area, the pressure that you apply goes down and you will eventually reduce the removal rate. So you need to understand at what point of time that you should stop, right, in order to maintain the flatness and not lose material. And this is how we characterize the planarity, right. So planarity is nothing but what is the angle between the global flatness or the local flatness that you have, and this strongly depends on the topography that you start with and the material that you have, and also the flatness that you are looking for, okay. So based on this, you could characterize the flatness, which is nothing but the topography over the length scale, right. So how far is these two flat surfaces are with respect to the topography that you have. All right. So as you keep on polishing, you would have very smooth surface, right, and you try to get local planarity done, right, and this is the intermediate stage. As you keep on progressing, you will get global planarity, right. So your planarization angle that we mentioned here, normally this comes when you have local planarization, right. So where you haven't really achieved the complete flatness. Local structures are flat, right. You are able to flatten out the sharp features, but your global flatness is not yet there. So that is where you get this local planarization and also planarization angle. But then if you keep on progressing in your polishing process, you will achieve global planarization, and typically your angle is going to be nearly 0. Okay? So once you get 0, that means you have achieved a complete planarity. Okay, so this brings us to the end of understanding CMP process, right. So what happens on the surface, how the CMP process progresses, right, starting from a topography, very large topography, very sharp features, and then you try to smoothen it, right, and then in the next step you get local flatness, and then finally you achieve global flatness. In order to achieve this, you need 4 components, as I said. You need the wafer that is in a moving or stationary holder, and then you have a pad that comes into contact with the wafer holder, and then you need a slurry, right. So that supplies the abrasives, right. So you need some particle in order to remove the material. So that slurry is supplied, and then finally you need a conditioner. So slurry in a fresh pad can work for some time, but then after a while the slurry is going to completely occupy your pad, and then your conditioner is the one that is required in order to remove all the settled particles and make the pad more abrasive. Okay, so the abrasive nature of the pad should be maintained, and that can be only maintained when you have the conditioner in place. Okay, so once you understand all these importance of this process, then you can design and then understand the implication of each and every step, which is something we will see in the next lecture.